Over the past 2 years, we've been exploring different ways to scale domain validation from multiple perspectives. And one of these ideas that we pursued was using the Tor network as basically a set of distributed proxies through which to do domain validation. As a quick intro to why this is even sort of interesting, since TLS is basically the workhorse of the encrypted internet, it's very important that the root underneath TLS is sufficiently secured. So all TLS connections use certificates to authenticate the server, and certificates are signed by a trusted third party, the certificate authority, and the identity of the domain can be validated by validating the certificate with the CA's public key. So a domain, of course, needs to obtain a certificate first. They do this by requesting it from the CA. With domain validation, the CA then generates like a high entropy random value and specifies the location on the domain's web server where this needs to be placed. And then once that's done, the CA can attempt to fetch this resource, check that the content matches the expected value, and then issue the certificate. This involves doing the DNS lookup for the domain and then sending the actual HTTP request through the internet to the server. And this sort of serves as proof that the one requesting the certificate actually has administrative control over that domain. If someone who doesn't have that kind of control requests a certificate, then we'd expect there to be a 404 for this request, and the validation fails. The problem is that since we're bootstrapping authentication here, all of this by necessity runs over unauthenticated protocols like plain HTTP, DNS, and BGP. And we just saw in the last talk, BGP still has problems. And so back in 2017 and 2018, there were a few works that showed that you can use BGP hijacks to sort of redirect the traffic, this validation traffic, to an attacker server, and then complete the challenge as if you were the one controlling this domain. So to the CA, it appears that way. And you can do this both with the actual HTTP request or with the DNS resolution, because DNS is also unauthenticated. You reply with a different IP address, and then you can do the subsequent HTTP request will land on your server. And then in 2018, there was work also done by our group that did the same thing with DNS cache poisoning of the CA's DNS resolver. So all of this kind of shows it's this domain validation process is quite vulnerable. Then in 2020, Let's Encrypt was the first CA to start validating from multiple perspectives. And without getting into too much detail, the sort of security of these BGP hijacks at some point boils down to these same prefix hijacks or equally specific prefix hijacks. And the thing you need to know about that is that these are topologically constrained. So depending on where you are in the BGP network, you can affect a certain number of ASes, but not maybe all of them, depending on where you are. So if you validate from multiple perspectives that are distributed in the BGP graph, then you can sort of tally these the different perspectives and decide on whether to issue a certificate. In 2021, there was work also done at our group that tried to tackle the challenge of attacking Let's Encrypt even with its multi-perspective setup. And while this is a lot more limited than it used to be, we've found that about like 25 to 30% of top 100,000 domains were still vulnerable to this, even with the 3 out of 4 validation that Let's Encrypt does through a combination of DNS and BGP attacks. So the lesson that we took out of this is that it's not enough that validators are distributed, but they should also be unpredictable. This kind of takes care of a lot of the attack surface, because if an attacker does not know which servers to attack in order to force the validation to succeed, then you protect from a lot of possible attacks. So our idea is basically that we want a large pool of validators that a CA can use, and for each validation, select a random subset to do the validation. And then the premise being, of course, that the attacker cannot hijack the entire pool, but can only hijack a few. And if he doesn't know which ones to attack, then he can't attack them. Now the question becomes how to scale this sufficiently and economically, because if all CAs, like Let's Encrypt, sort of host these validators in the cloud, and you need a large pool of validators, this becomes quite expensive. So our thought was maybe we can leverage Tor network as a set of proxies to do this validation through. Just as a comparison, we sort of tried to crunch the numbers based on the budget breakdowns that Let's Encrypt used to publish. They haven't done this for a few years, but we sort of looked at what they said they were spending on hosting, and their costs have sort of increased in line with the number of certificates that they issue per day. And we sort of extrapolated this to present day. And most importantly, we also need to account for the fact that they deployed multi-VA after the last budget breakdown that they posted. So I think it's safe to assume to at least double the costs once they went from a single server to 4 servers. And so it seems that it would cost about $2 million per year to run this. And now that the CA browser forum is looking to sort of standardize this MPIC, this multi-perspective issuance corroboration, other CAs are also required to set up more vantage points from which to validate. And so we were looking for more economical ways to do this. Not going to go into all of the different ideas that we went through, but we decided to focus on Tor as a subject of study because it is free, it has high capacity, there are many nodes to choose from. It's already monitored for malicious activity, which gives it sort of a benefit over setting up a whole new network to do this with. And so what this roughly looks like, we created a proof of concept. We wanted to get this close to production, so we added like a web server with a little API. You can submit a validation request. This then gets processed in parallel by the different workers and gets sent through the Tor proxy into the Tor network through a 2-hop circuit rather than 3. We managed to cut it down to 2. 1 is unfortunately not feasible, but 2 is at least less overhead. And we run our own little circuit management software, which ensures that the choice of exit nodes is random, and for each validation, that the exit nodes that are collaborating to validate this are sufficiently distributed. Then we, of course, also profit from the fact that Tor actively encourages nodes to use their local DNS resolver. So we also have sort of distributed DNS resolution as part of this process, since DNS is also vulnerable in this scenario. And we built this as a container just because it allows for very easy horizontal scaling, and it allows us to track the network input and output in order to see what kind of load are we putting on the Tor network. And I'll get back to that in a second. So what we did to evaluate this is we initially sent in the top 100,000 domains, sort of sent them into our proof of concept to validate, and then our app sort of logs which IPs each domain was resolved to, which exit IPs, or what are the IPs of the exit nodes that we use to validate. And so we can sort of reconstruct which paths the validations took, and yeah, we evaluate this in terms of path diversity. This is sort of, we have two metrics to capture this, because we asked ourselves, so in the absence of targeted attacks on these validators, since we're saying these are randomized, an attacker doesn't know who to attack, what is the remaining attack surface, and can we, what can we do to improve that? And we try to capture this in like a single metric via the path overlap. So if we consider the paths to the BGP networks as a set of hops of ASes, what is the relative sort of pairwise overlap between different validators? And then a different, slightly more intuitive metric is to ask what is the percentage of validators that a given AS can intercept. Specifically, how many ASes are there that can intercept all of the validators? So even without BGP hijacks or like messing with the routing in any way, there are going to be ASes which are just well positioned in the network through which a lot of traffic is just going to transit. And if we have ASes, where all the network, where all the traffic from all these validators goes through, those can still, manipulate this validation result. So we want to keep that as minimal as possible. And we answered these questions with a routing simulation. We reconstructed the BGP network from BGP collector data and informed the sort of the pathfinding with the CAIDA AS relationships data set. So we can do Gao-Rexford aware pathfinding. And then we basically, both for the Let's Encrypt deployment and the random set of Tor nodes that we selected, we can find out which AS each target domain and each validator is in based on the IP address. And then for each target, we can see what are the paths that are being taken and how do they overlap. And then we can compare this between the Let's Encrypt deployment and the Tor deployment. One of which has static points; they stay the same, and the validator deployment, has randomized validator nodes. And we see that the path overlap is overall much lower compared to Let's Encrypt. That's this in orange. That's Tor. Let's Encrypt are the blue columns, and we also created a sort of hypothetical deployment of 30 different locations on the AWS network to compare whether we can get a similar metrics using the cloud if we do decide to do that instead. And that actually looks very similar, but you need a lot more nodes than are currently being used. Similarly, for the sort of percentage of validators that can be intercepted by a given AS, we check this for different numbers of validators. So for each validation, we can determine how many nodes do we use to validate. And increasing this number is a very easy way of increasing sort of the path diversity and lowering the number of ASs that can intercept all of the traffic or intercept a sufficient amount of traffic to still force a fraudulent validation. Okay, quick note on sort of performance. We looked at how many validations can we do and how long does that take. So from like a user perspective, it takes about on the order of a few seconds to do a validation. So that's very similar to what you expect currently with using certbot. And in terms of total throughput, we did a few experiments to see how does this scale. We got to 12 validations per second, which is still an order of magnitude away from what the global certificate volume is, but we can demonstrate that it's very simple to horizontally scale this, so that we don't see a reason why this can't be deployed in production or in a larger scale. So an obvious question becomes, what about the load on Tor? Aren't we sort of abusing the bandwidth that Tor offers? And we wanted to see what would the bandwidth usage be if we did this for the entire global certificate volume. And so based on certificate transparency logs, we saw there are about 104 certificates being issued every second. Based on our traffic measurements from our container, we see about like 47 kilobytes of data for each validation that's being required. Then we sort of thought, okay, these are just like the certificates we see in certificate transparency are all sort of successful validations. Let's safely double this for failed attempts as well. There are redirects that need to be chased during validation, HTTP redirects. So we doubled this again. And then we need to consider that this traffic is going in and out at the exit node as well as in and out at the entry node. So taking ingress and egress traffic into account, we end up with around 600 to 700 megabits per second of traffic that would be required for all validation traffic globally to go through the Tor network, and about 300 megabits going specifically through the exit nodes, which are much more limited. However, if we look at the Tor metrics, so basically the official bandwidth that's being advertised by Tor nodes, and compare this with the consumed bandwidth, we see that this bandwidth estimate that we created is just a tiny fraction of the bandwidth that is still available, at least according to Tor. So depending on how accurate these numbers are, there's still a large margin for error where you can say we're definitely not causing an excessive load on Tor with this. Last question I want to sort of preempt before is, what about malicious nodes? So okay, we're using these volunteer nodes to do validation. Can we trust those nodes? You can, of course, as an attacker, add nodes to the Tor network, or at least attempt to. I want to see, okay, what is the probability that an attacker can force a validation by just using malicious nodes rather than hijacking traffic? And so that looks something like this. It's very close to the hypergeometric distribution, but it's actually slightly lower. And you can see that K, so the number of validators that you use per validation, is a very useful parameter to decrease the chance that an attacker can manipulate the validation. So in 2020, there was an example where there were about 1,500 exit relays in the network, and an attacker managed to add around 1,000 more. And so we kind of ran the numbers through this. If we were to use just 3 validators per validation, this looks pretty bad. This looks like a pretty good chance for an attacker to manipulate validation. But as we increase the numbers of validators we use, this sinks very quickly. And this is also something that we can adapt dynamically. So if we feel like the Tor network is under threat, we can up the number of validators we use per validation. And updating this to like the number of Tor nodes we have today, it looks actually even better because the relative advantage of the attacker is lower. And with that, I'm going to conclude. For those interested, I'll point you to the GitHub repository where we have all of this stuff open sourced. And feel free to email me if you have more questions about this. Thank you.